Alright, hello chemists! Welcome to Electrochemistry lecture number 1. Are you excited? Alright, we're going to go over voltaic cells, voltage, and hopefully standard reduction potentials and standard cell potentials in this video, but we might have to wait till the next one. So let's start with talking about electric current. What is electric current that travels from its source, where we're producing electricity, to where we use it? Electric current is the amount of charge that passes through a cross-sectional area of a medium, typically a wire, per second. So current, I, is measured in amperes, A. Small q is the charge, measured in coulombs, capital C. And T, time, is measured in seconds, S. Okay? F is the Faraday's constant, which is 96,500 coulombs per mole of electrons. So that's the amount of charge per mole of electrons. This equation is given to you on the free response section of the AP exam. So let's do a quick practice problem with electric current. So how much charge passes through the cross-sectional wire that is carrying 0.987 amperes of current for 12.3 minutes? Okay, part B, how many moles of electrons pass through the cross-sectional area? Okay, well the first thing we have to do is calculate this into seconds. Okay, and then we are asked how many coulombs we have, or how much charge passes through the wire. So this is how many minutes, and we have the current itself, so charge per second. So this is how many coulombs are traveling through this wire, okay, in 12.3 minutes. And the next question, how many moles of electrons is this? Well, this is where we would use Faraday's constant. Here's how many coulombs pass through in 12.3 minutes. We can multiply this by the Faraday's constant, 1 mole of electrons over 96,500 coulombs, and we have 7.54 times 10 to the negative 3 moles of electrons. All right. Now, so hold on to your thinking from the current, and we'll come back to what that means a little bit later. So, spontaneous redox reactions. So these are oxidation reduction reactions that happen spontaneously. Okay? So if we put a strip of solid zinc into a solution containing copper ions, the copper ions will accept, here's a copper ion, and it will accept 2 of the electrons from zinc. So that copper cation accepts the electrons from here. The copper cation is reduced because it gains electrons. Reduction is the gain of electrons. So the copper ion is reduced to copper, and the zinc, the solid zinc, is oxidized. It loses those electrons. Okay? So then copper solid will replace the zinc, and now we have zinc ions in a solution. Alright, so let's look at writing a balanced redox reaction. So when you see the solid metal placed in a solution containing metal ions, it will always be this type of redox reaction. Okay? So on the AP exam, anytime we have a solid metal placed in an ionic solution, it will be a redox reaction. The reaction will continue. So we don't need to look at the activity series to see what will react with what. It will react. So if a copper penny is dropped into a solution of silver fluoride, okay? So we'd write the copper penny as a solid, Silver is the cation. Silver is one of the transition metals that always only has a charge of +1. Okay? And the copper solid will be oxidized. It will lose the electrons, and the silver ion will be reduced. It will gain those electrons, and then make sure that we balance it, because the charges and the atoms need to be balanced. Right, moving along. So galvanic cells. So these are typically the cells that we'll work with. This is one type of cell that we will work with in electrochemistry. So galvanic cell is a device that transfers electrons away from one of the reactants to the other through a pathway. So it's the opposite of a direct transfer, because it has to go through a pathway, which we'll show you. These are always spontaneous, so delta G is less than 0. And chemical energy is converted into electrical energy that moves electrons. So we have an oxidation-reduction reaction that is causing electrons to move, and which creates a current, and then we'll relate that to voltage later. Alright, so here is a typical model of a galvanic cell. So this is the same as the first reaction that we looked at, only it's split into two half reactions. We have the oxidation half reaction over here, and we have the reduction half reaction that's happening over here. The galvanic cell forces the electrons to travel through a wire in order to complete the oxidation reaction that happens in this half cell and the reduction reaction that happens in this half cell. Each half cell has a solid electrode immersed into an electrolytic solution which contains ions. So the anode is the electron where the oxidation takes place. Alright, so to come back to this, the anode is where the oxidation half reaction happens. So remember, oxidation is loss of electrons, okay? And the cathode is where the reduction happens. Reduction is gain of electrons, okay? Oil rig. Now, the reactions at each half cell, let's look at those. So zinc, the metal, loses 2 electrons as the solid zinc atom enters into and becomes an zinc ion. Okay? So here we have an oxidation of a loss of electrons, so the zinc metal becomes a zinc ion. What also happens here is that the mass of this anode is going to decrease because these zinc atoms are now becoming ions. Conversely, at the cathode, the reduction reaction, the mass is going to increase because now we have copper ions that are now becoming solid copper. So the cathode mass will increase, the anode mass will decrease. So as this reaction as it continues, the mass of the anode decreases, mass of the cathode increases. Now let's take a look at the salt bridge. So before any of the reactions can take place, the oxidation half cell is electrically neutral. Notice, zinc ions and sulfate ions are equal. The reduction half cell is also equal because you have copper ions and sulfate ions. Now these solutions need to remain electrically neutral for the reaction to continue. This is accomplished by the salt bridge. The salt bridge is a U-shaped device, usually has solutions of an ions in a gel. And as each zinc ion over here enters the solution at the anode, the sulfate ion also enters this oxidation half cell in the solution to maintain neutrality. As each copper ion leaves the solution to form the solid and bond with the cathode, 2 sodium ions have to enter the solution and maintain neutrality here. So as the sulfate ion leaves the salt bridge at the oxidation, so as the sulfate ions leave the salt bridge into the oxidation half cell, sulfate ions are sucked into the salt bridge from over here. As the sodium ion leaves the salt bridge, sodium ions here, as it leaves and comes into the reduction half cell, the zinc ion enters into the salt bridge. Okay, so this acts as a battery, and this is similar to how a battery works. The battery dies when there is no more solid zinc at the anode, or when the reduction half reaction cell runs out of copper ions. So when the copper ions are empty, or when the zinc ions are zinc atoms, there are no more, then the battery dies. So this is how a battery works. Now, you notice that we have the charges here. We don't need to be able to label the charges of this for the AP exam, but just so you know, if we have electrons leaving an area, that's the negative charge. Electrons are attracted to the positive charge. So in this way, the cathode is positive, the anode is negative. Okay. All right, as the reaction proceeds, I already mentioned the mass of the anode decreases, mass of the cathode increases. Okay, so solid zinc loses 2 electrons, falls off the anode as it becomes aqueous. And the opposite happens at the cathode. Salt bridge in writing. One thing to consider here is that the ions from the salt bridge must not react with the ions in the electrolytic solution to perform as precipitate. Otherwise, those ions will not maintain the neutrality, and once again, the battery will die. So here's another photo of image of the salt bridge. In this diagram, the sulfate ions are moving into and out of the salt bridge. As the zinc ions enter the oxidation half cell over here, a sulfate ion also enters into it. At the same time, a copper ion gains 2 neutrons and transforms into copper. So you can kind of see how this works back and forth. Always maintaining neutrality in the solution. All right, so if everything doesn't remain neutral, so in this case, if the sodium ions do not enter the solution, the cathode will have an overall negative charge, and this would repel the incoming electrons. So if we don't have neutrality here, those electrons will be repelled by this. So cations always move toward the cathode in the salt bridge. Cations move toward the cathode in the salt bridge. Also, the electrons move toward the cathode because they're electrons negative, attracted to the cathode. Cation, also positive, so attracted there. And that's a good place to stop.